So Brad, we're here at the Flux Tower. Why don't you tell our viewers what they're looking at in the background here, and then tell us why it exists.
What we have behind me is a 50-meter plus carbon greenhouse gas emissions monitoring tower. It's been here, this one's been here about 2.5 years, and the purpose of this tower is to collect data on the carbon, methane, and water vapor being emitted from this natural forest. Surrounding us is a 130,000 hectare peat forest, which this tower is representing as a control. We have two other towers on the Kampar Peninsula. One is in plantation, and the third is in a different land use of mixed forest types, combination of natural forest, plantation, and community agricultural uses. The purpose of the towers is this: to identify what are the carbon and greenhouse gas emissions occurring from these different land use types. And once we have the answers to those emissions, then this will help us better define the activities we as a company can do to mitigate those emissions from the forest and from the plantations. So from a historical perspective, Indonesia is a huge greenhouse gas emitter. 50% of their emissions come from land use change, from forestry and other agricultural uses. From the forestry side, the majority of the emissions come from peatlands. It comes from forest degradation and deforestation. It comes from conversion of forest to agriculture. But the greatest proportion comes when those peatlands catch on fire. So fire is a major cause of greenhouse gas emissions. April has numerous programs to try to minimize these emissions. We have a fire-free village fire prevention program. We are conserving natural forest at a 1-for-1 rate with our plantations. We're almost achieved that now, about 83%. And we're doing tremendous amounts of work in restoration and conservation of our peatlands through best management practices. One of those best management practices that we're now implementing are these greenhouse gas monitoring tower programs. So what the purpose of this program is to monitor CO2, methane, nitrous oxide, and water vapor from the forest and other land use types. We need to identify all the different pathways that emissions are occurring from the forest and the land. Once we have those identified, we can then take mitigative actions on how to reduce those. So on the Kampar Peninsula, which is our study site, which is 700,000 hectares in size, we have 3 greenhouse gas emission towers, like I explained a moment ago. Each of these towers costs about $1 million to construct. On top of the tower is over $250,000 of equipment that is actually doing the monitoring. We have teams that visit each of these towers once every 2 weeks at a minimum to maintain, clean, and download the data. Trying to go the other direction. The equipment on top is collecting data 10 times every second. We make 864,000 observations every day. From that data, we take one reading every 30 minutes, so 48 observations per day, and we use that data for analysis. And again, this tower represents a minimum area of 200 hectares. Now, this technique of using these towers is new to Southeast Asia. It's very commonly used in temperate climates, like in Europe and North America. As an example, the Ameriflux network of towers similar to this has over 336 sites across the United States. In Southeast Asia, however, where land use change is a major cause of emissions, there's only about 10 towers. And there's only 8 towers in Indonesia. 4 of these towers are on peatland. 3 of those peatland towers belong to April. So what we're monitoring is the total removal or emissions of these gases from the forest. Looking at the primary emissions from the canopies, looking at the soil emissions and the root emissions and the microbial emissions. And we need to understand the total emissions in order to have a complete picture of this data. So what have we found? Well, basically the emissions in the forest and the plantations vary every day. In the night, the plantation is a source of carbon dioxide. Why? Because the trees are not photosynthesizing. They're not absorbing carbon. They're emitting carbon because there's no sunlight to drive their motor, in a sense. But during the day, when there's sunlight, photosynthesis is active, and therefore carbon is being sequestered into the plantation trees. So the graph looks something like this. During the nighttime hours, there are carbon emissions. During the daylight hours, there's carbon sequestration. So there's actually more emissions occurring during the day than there are sequestering during the number of hours each day. But the amount of sequestering occurring during the daylight is quite significantly different than the amount of emissions above the zero line. Another way to look at this is looking at cumulative emissions over a period of time. These graphs here which demonstrate the natural forest which we're in and the emissions that occur on a month-to-month basis accumulated over time. In this graph, you can see that during the dry season, carbon emissions continue to increase day to day, month to month. Why is this happening? This is because the water table in the peat is dropping due to a lack of rainfall. So the natural forest in the dry season is a net emitter of carbon, which may be surprising to some people. But when the wet season begins in November, December, January, and continues through the first half of the year, you begin to see a net decrease in carbon emissions. Why? Because the water table is increasing, coming up to the surface as a result of heavy rainfall occurring every month. So the natural forest fluctuates in its carbon emissions and sequestration potential. Compare this to the plantation, same period of time, accumulative graphic. This is preliminary data. It's not finalized. It's not definitive. This is only about 18 months of data that we're showing. Looking at the plantation for the same basic period, looking at the dry season with a young seedling planted in May and growing, not just the seedling, but the whole compartment, we're seeing carbon emissions increasing during the dry season as water tables are managed. Rainfall is still low, but because in the plantation we're managing the water table between 40 and 90 centimeters, so there's always water and moisture in the peat. But we're finding, though, that at about 9-10 months of age, we're seeing that the emissions are beginning to decrease. Why is this? Well, one is because we've entered into rainy season, but a second reason is because the trees are getting older. They're growing faster. They are sequestering carbon in the young, healthy trees that are growing at about 10 months to a year old. And we're seeing a trend where they continue to decrease. We don't know what the trend is beyond a year and a half. We have to collect more data to see that. But this is a positive sign in comparison to natural forest. In basic summary, we're not saying one is better than the other. They both have differences. We're saying we're collecting the data to find out what those differences are so we can have the true comparison. We need 5 years, basically the rotation of the acacia, to come up with that comparison. But another interesting element to this is the methane emissions. Methane is another greenhouse gas or global warming gas emission. It has over 86 times more global warming capacity than carbon over a 20-year period. What we're finding with methane from our towers is this, that methane emissions are highest in the natural forest and lowest in the plantation. they're highest in the natural forest because methane is emitted when the peatland is flooded, when the roots are inundated with water. They're anaerobic in a sense, yeah? But the plantation has lower methane emissions, a lower greenhouse gas warming potential, because the peat soil is slightly drier than what it is in the natural forest. And what we're finding basically is that the natural forest has twice the methane emissions of a plantation. Again, we're not saying one way or another. What we're saying is these are huge differences. You have to look at it over a time scale, and at the end of that time scale, we can begin to do analysis.
Great, thank you.
Yeah.